Welcome, ninth grade extended students. Today we are going to talk about identifying isometries based on their fixed points. In exercises 18 through 23, we experimented with reflection over 4 lines, and we tried to figure out what kinds of isometries those created. We looked at all different kinds of situations where perhaps the lines were parallel or 3 were parallel, 1 was not, to identify whether or not these isometries could be simplified into ones that we already know. So in a moment, we're going to look and summarize what we discovered. There are 8 cases. There's no need to memorize all of them. I will talk about how you can have some idea about what type of isometry it is. And again, we're going to start to identify these based upon the number of fixed points. So the first case involves 4 lines, all of which are parallel. Now, this turns out to just be a translation because if you can imagine, when you reflect over a set of parallel lines, we just take our figure and translate it. Then we reflect over 2 more parallel lines and we translate it again. So overall, I could have just done 1 translation from the first figure to the final figure. And again, you experimented with this in exercise 18. In case 2, I have 3 lines that are parallel and 1 of which is not. This always turns out to be a rotation. So if you can imagine, I have my figure translating over these 3 lines, and then when I reflect over the line that's not parallel, what happens is I end up rotating my figure. Now, the way you can have an idea of whether this will result in a translation or a rotation is to imagine that your figure is moving. If it ends up being in the exact same orientation, meaning not twisted or rotated around, it's a translation. But in this case, every time I reflect over these lines, regardless of the order, I end up with a figure that is not in the same orientation. So therefore, it just creates a rotation. Here's another case. In this case, I have 2 sets of lines that are parallel, and those parallel lines are perpendicular to each other. Regardless of the order in which you do the reflections, this creates a translation. So if you can imagine, take my figure and reflect over these 2 parallel lines, it translates it, and then reflect over these 2, it translates it down. So I will end up having my figure in the same orientation, and I could have accomplished the same thing just through a translation. In the 4th case, I have 2 sets of lines that are parallel, but they are not parallel to each other, and also they're not perpendicular to each other. This will result in a translation or a rotation, and it depends on the order in which you do these reflections. In the 5th case, I have 4 lines, and L1 and L2 are parallel, but they are not parallel to any of the other lines. So you can see it, this is represented in this figure right here. Depending upon the order in which I do this, I will either get a translation or a rotation. And 6th case, I have all 4 lines, none of which are parallel, no 2 of which are perpendicular. And we experimented with this in exercise 23. And this also creates either a translation or rotation depending upon the order in which you do the reflections. And the 7th case, same thing, results in a translation or a rotation. Depends on the order in which you do the reflections. No 2 of these lines are parallel, and I have exactly 1 set that is perpendicular. In the 8th case, you did an experiment with this, but in this case, none of these lines are parallel, and I have 2 sets that are perpendicular to each other. And in this case, it would result in either a translation or a rotation. So those are all the different options with 4 lines of reflection. And again, if your figure ends up in the same orientation, it'll be a translation. If it looks like it was twisted or rotated, it is a rotation. Now, all of those were even isometries, meaning I was reflecting over an even number of lines. Odd isometries occur by reflecting over an odd number of lines. So every even isometry of the plane is the composite of two reflections of the plane. So if I have a reflection over an even number of lines, I could have gotten the same result just by reflecting over two lines. Every odd isometry of the plane is either a reflection or the composite of three reflections. So in other words, if I have an odd number of reflections, I could simplify that to either one single reflection or the composite of three. The three reflections for the odd isometry is called a glide reflection. This results when I have two lines that are parallel and one that is perpendicular to the two parallel lines. So you can see what happens is you translate and then you rotate. So that's why it's called a glide reflection. Here's a little bit of vocabulary for you. This involves translations relative to a line. So if I have a plane and I have a line M, for all translations of pi, where my translation is not the identity mapping, my translation is parallel to M if and only if A, when I join my line between my point and its image, is parallel to M. So let me show you what I mean by that. So if I have a point here, A, and it translates to A prime, and I consider the line that joins those 2 points, I would say that this line M is parallel to that translation, provided that M is parallel to the path of translation. If my translation path is perpendicular to a line, then I say it's perpendicular to that translation. So if I look at a different set of points, let's call it B and B prime, and I consider the line that joins these 2 points. Again, my translation is going from B to B prime. I would say my line is perpendicular to that translation if the line is perpendicular to the path of the translation. Okay, it's time to give a formal definition to our glide reflection. It is the composite of a reflection and a translation where the reflection is over a line that is parallel to my translation. So watch. If I am taking my point A and I'm moving it to A prime, the line of reflection has to be parallel to that path. So we'll call this M. So my figure would translate in this direction and then reflect over my line M. And that is the formal definition of a glide reflection. ISO 4 is actually very helpful to us. It minimizes the type of isometries that exist. So for each isometry f of the plane pi, if f is even, then f is either a translation or a rotation. If f is odd, then f is either just a reflection or it's a glide reflection. Now, identifying the type of isometry can be done quite easily through locating the fixed points. So there are different options for even and odd isometries. If there are no fixed points, then if it's an even isometry, it's a translation. Remember, translations other than the identity mapping have no fixed points. If it's odd, then it's a glide reflection. If there's exactly one fixed point, if it's even, remember a rotation has exactly one fixed point, that's its center, and there are no odd isometries that have exactly one fixed point. If there are at least two fixed points that are all collinear, if it's an even isometry, my only choice is the identity mapping. If it's an odd isometry, it must be a reflection. Remember, the fixed points of a reflection are on the line of reflection. If there are at least three non-collinear fixed points, then if it's an even isometry, it's the identity mapping, and then it can never be an odd isometry. Now, while you did not need to memorize all those different cases I discussed earlier, this chart is very important and you should absolutely know that. And now I'd like you to do these problems. They are posted in Schoology. Have a great day.